And working in quantum information and quantum gravity.
Yeah, kind of.
He already gave one informal talk, and today it's more formal about black hole information paradox.
Yes, thank you very much. Thank you for having me here. So I'm going to talk about my work on the black hole information paradox. It's in collaboration with Oscar Dahlsten and Leonardo Modesto. So Oscar is a quantum information theorist, and Leonardo is a quantum gravity theorist. So, okay. So black holes are defined by their horizon. Black holes are objects with horizons. So it's an object with a surface which you can't escape if you are trapped. There are black holes with singularities, without singularities. All kinds of theories predict different things, but what defines a black hole is a horizon. Now, in the year 1975, it was shown by Hawking using a quantum field theory on curved space-time that black holes emit radiation. So there are pairs of particles created near the event horizon, one with negative energy, which is eaten by the black hole, and one with positive energy, which is emitted far away. You can also see it by computing the stress energy tensor, and you find a negative flux going inside and a positive flux going outside near the horizon. Now, these are not exactly particles because their wavelength, the typical wavelength is like the size of the half of the black hole horizon or something, maybe the black hole horizon's radius. But they are usually approximated as particles. And anyway, there are excitations in the quantum field. Now, so what Hawking showed, what Hawking did is he took a black hole. Are you all familiar with Penrose diagrams? A little? So he took a black hole, and he took a collapsing shell, collapsing null shell, so it's dust collapsing with the speed of light and forming a singularity, which forms a black hole. Here there is a parent horizon, and it joins the event horizon later. During this scenario, there's here a Minkowski spacetime, and here there's a Schwarzschild spacetime. And then you can compare the definition of your vacuum in these different patches of your spacetime. Here your vacuum is the normal Minkowski vacuum we know. Here the vacuum is another vacuum. So they call it zero out, and this is zero in. This is the in region, this is the out region. Then he compared the out vacuum with the in vacuum and showed that there will be outside, there will be radiation, in the out region. And this region, he calls it int. So there will be, what he derived is a state of the radiation. He showed that there will be pairs of particles created, and they will be in a state which is a tensor product over 1 minus exponential minus 2 omega big M, which is the black hole mass, and then sum over n sub omega. So for each of the terms of the product, there is a sum over the number of particles with this energy omega, exponential minus omega big M times the number as well. And then there is n omega int and n omega out. So for each energy, for each energy omega, there's n omega particles inside the black hole and n omega particles outside the black hole. Now, what's interesting about this state is that you look at the outside radiation, you find it in a mixed state. So if you compute the reduced density matrix, rho out, you find it different from u out squared. So the state is mixed at the end of the evaporation process. And it's mixed regardless of what is the state of the matter forming the black hole. So, I mean, first, intuitively, you can see the state of the radiation. It does not depend on the state of the matter forming the black hole. It only carries information about the black hole mass and says nothing else. So even if I have a big detector and I compute, like I collect all the radiation and process it, I know nothing about the black hole matter. That's just for the physical intuition, but also you look at the radiation state, you find it mixed, in a mixed state. So you can imagine I have dust, and the dust is in a pure state, and then that dust collapses and makes a black hole. So I have dust in a pure state, and then it collapses and makes a black hole. And then that black hole starts to emit radiation. And then after emitting more radiation and more radiation, as it emits radiation, it loses mass until it fully evaporates. So we'll end up with only radiation particles, and they are in a mixed state. Yeah.
Now, now putting on side the evaporation,
yeah.
Is there a process that will start with a state outside, as you put dust in the pure state, and then unitarily nicely show that you end up with this state, which then maybe evaporates, and there is a problem. But I just am asking about this kind of pure state transforming into the entangled state between input and output modes. I know that people start with this and then say, oh, now evaporates and
yeah.
unitarity is lost. But I'm asking the step before that.
So you are saying something starting with this
Yes.
and ending with this state.
Yes.
Yeah. You can actually easily check, we can do later, that the process from here to here is unitary. Yeah. So until here, it's not a problem.
Yeah. I understand it's unitary.
Yeah.
It's pure
Yeah.
state, but
Yeah.
I mean, this has been done. So.
Yes. There is a matrix which actually does create all these particles. And it's a unitary matrix. So now, if you look at this state, it's a pure state. It has the int mode, so there are particles here, and they have partners outside, and they are all entangled with each other, I mean in pairs. And the whole state is pure. Also with the black hole state, if we write it somehow, then they will be together. It's completely fine. You can't see the problem. But the problem is when the black hole fully evaporates, then there's the int modes do not exist anymore to purify your out state. And that's the problem, because you end up with a state, with a mixed state, even though you started with a pure state. And as we know, one of the basic axioms of quantum mechanics is that closed systems evolve unitarily. So this is the information paradox. Please feel free to ask at any moment. Stop me and ask as much as you want. So, questions so far? Yeah?
Just one question. If you have the black hole,
Yeah.
I mean, the state may be fine still when you have the interior modes, but practically you have no access to them.
Right.
So don't you already have the problem?
No. Yeah, that's a very good question. And the answer is no, because I have a system, and I split it into two. I have access to a part of it. I don't have access to the other part. And the state of the system to which I have access is mixed, but the state of the whole system is pure.
But how would you check?
Yeah, right. So at least we have, we believe that closed systems evolve unitarily. So even when you don't have access to a system, to part of the system, you know deep down that, okay, when I include it, I will have everything unitary and clean. And that's what happens all the time in physics. However,
You measure the output and then you fall inside.
yeah.
I don't know.
Yeah, you can do this, I mean. But for any system, for any big system, when you actually have access to part of it, if the system is entangled, then the part will be in a mixed state, but you know it will be purified if you include the whole thing. Unless unitarity is violated even outside a black hole or something that's even like could be really bad, but we haven't gotten so far yet.
Comment.
Yeah.
Also I mean, the entire calculation happens on a classical background.
Yes.
So at some point, quantum gravity itself needs to be taken into account.
Yes.
As well.
Yes.
And so there are regions in this diagram, I mean, close to the singularity, where
Yeah.
we cannot trust the theory.
Right. That's true. So.
The diagram may be different, or it may not even make sense to have such a diagram, because the Penrose diagram is a representation of a classical solution of one classical solution of Einstein's equations.
Right.
For a class of solutions of
Yes.
Einstein's equations. But in quantum gravity, or in quantum theory, we don't have just one solution.
Yes.
We have superpositions, or even the notion of a classical space-time may not
That's true.
make sense anymore.
That's true.
So drawing such a
right.
picture means to assume already that a classical space-time geometry exists.
Yes and no. And the reason is, so actually, that's a very good point, and people have been saying this for a long time, since Hawking's computations. First 10 years, maybe people were just suspecting, doubting his computations and taking fewer approximations, and then it still gives always the same result. Then people said, okay, but there's quantum gravity. Quantum gravity, for example, can stop the evaporation process. It can give remnants. But then the thing is, this can be done for a huge black hole. And the radiation, you can derive it. It's just from the region near the horizon. And that's almost flat for a large black hole. So then you expect, at least there, the semi-classical approximation to hold perfectly. Then the problem is, okay, it keeps, so you imagine a huge black hole, and it keeps evaporating and evaporating, and then it gets small. There, when the black hole is like Planck mass, then you can actually expect quantum gravity effects to have a large impact, to be significant. And then people talked about remnants. So one of the approaches of the paradox are black hole remnants. They can be stable or unstable. Remnants are just when the black hole evaporates, and then when it reaches like a small, when it's of the order Planck mass, then some people expect the quantum gravity can stop the evaporation. So I have a small thing left, which is of Planck mass, and that thing can still carry the information or can purify the state of the radiation. But this is unlikely, at least in most people's opinion, because you can have a black hole of the size of the universe, and it evaporates, and it keeps evaporating until it reaches the Planck mass. So all that matter, all that radiation, is impossible, or it seems impossible, to be purified by such a very, very small remnant at the end. You need as many degrees of freedom in the remnant as there is in the universe-sized black hole, which is maybe possible in some exotic theories, but it's not very popular. So there are remnants which are stable and unstable. The stable remnants are those, it's just like saying there's a black hole, it's still a black hole, but it does not evaporate anymore. And unstable remnants say there's something, the black hole, when it gets very small, then it stops being a black hole anymore, and just matter is just spilled out. So this is one of the theories. Then the challenge will be to actually find some quantum gravity theories that predict remnants. And there are some attempts in loop quantum gravity and other theories. Another thing which was proposed a long time ago, maybe in 1993, by Don Page. So Don Page studied large systems in randomly generated pure states. Just no black holes, just any large systems in randomly generated pure states, and started to take small subsystems out. So there's a large system here with dimension b, and a small system here with dimension r, small r, and then b and times r is the total dimension and is constant. So you keep taking stuff out, and you study the entanglement entropy of this subsystem as it increases, as it grows. He showed that, so he didn't study exactly entanglement entropy, but studied purity, which is trace rho squared, and then using some inequalities for Renyi entropy, you can relate it to the entanglement entropy. If anyone is interested, we can write down, but that saves the time now. He showed that for such systems, the typical behavior is that the purity or entanglement entropy with the log of the dimension of the subsystem, there's a stage where it grows maximally. It grows as much as it ever can, and then it reaches a point which people call page time, and then it starts to decrease as much as it can ever do. So here in this region, there's no information in those particles that I'm taking. It's like they look completely black. I mean, they have no information encoded there. But then here, there's as much information as one could ever have. So it's like saying that the early, so anything before the page time, we call them early particles. And after the page time, there are late particles. So anything which is early emitted, those are not entangled with each other, not correlated. They are still correlated with the big system, with the large system. But then the late ones, they are actually, typically, they are entangled with the early ones.
But this state is not a random state. It's a very typical state, two-mode squeeze state.
Yes, this is a very typical state, yes. Yes, yeah. So he's not exactly trying to study this. At the beginning, he was just, okay, I have a system in a box. I don't know what it is. What's the typical behavior? And he argues then when he applies it to black holes, he says, okay, what is a black hole? It's a quantum state. It's a quantum system. And then it should behave like other things. It's not really a proof. It's just what to expect. It tells you what to expect. So yeah, if a black hole is a quantum system, it should behave like other quantum systems, typically. Yeah. Especially that you can control the state of the matter which collapses and forms the black hole. But yeah. Then what he did, so this tells us kind of what to expect, but also we don't know how it happens, right? Because even if we know this, I mean, the state of the radiation is still mixed and everything. It's not entangled with each other. The out particles are not entangled with each other. And yeah, what he said is this teaches us that, or reminds us that if out particles, if the radiation particles, if the late particles are entangled with the early particles, if late radiation is entangled with early radiation, then the full state of the radiation can be pure. And we know this, but he kind of said this is what to expect. Now, later, maybe 10 years later, or a bit even more, it was shown by Mathur. Yeah.
This, like, if we would agree that the state is really random,
Yeah.
would this be an explanation that we don't worry about evaporation because anyway we get all information before?
We would still worry because the state we have
It's not like that.
is not like that. Yeah.
Okay, but if it were like that, would it be?
Yeah, it's fine. Perfectly fine. Yeah. So now all the attempts in the whole community of like people who work on this is actually to try to derive that curve in many different ways, but to show that black holes actually have a way to let out the information in this way.
This would very much depend on the state of the time.
Yeah, exactly. Okay, so then it was showed by Mathur that so if this is an early radiation particle, it's already far away, and this is a late radiation particle, still near the black hole. So these guys cannot be entangled with each other because each of them is already very strongly entangled with its partner inside the black hole, as it's clear in the Hawking state. And if you assume all this amount of entanglement, the amount we know here, and the amount we need here to purify the state, you can easily show that you violate, I mean, this violates the entanglement monogamy, or more, if you want mathematically, you actually violate strong subadditivity of entanglement entropy. Yeah. So then people started to come up with ways. For example, people introduced the so-called firewall, which is a high energy surface at the event horizon, extremely high energy surface, which can supposedly break the entanglement between inside and outside modes, allowing the ones that are outside to the early and late radiation to be entangled with each other.
Epicycles of epicycles.
Yeah. So, but I mean, it's quite. It was very popular at some point, but then it has problems. First, it's quite exotic, and we don't know, at least not to my knowledge, we don't know a theory which can predict such things, such firewalls. And even if they are, we are not sure they can break the entanglement. And even if they do, this doesn't make it necessary that early and late will get entangled with each other.
Can you, like these two particles in the inside, now they can interact with each other, and then can you not have something like entanglement swapping, and then like
Yeah.
what happens with?
You can actually.
Okay.
You can actually. That's my paper. Thank you. That's my paper. Almost. So the entanglement swapping will happen when they interact with the black hole matter. So yeah, this is the matter objection and the firewall and etc. So now we come to your idea, and here's what we do. So we simplify the model very, very much. First, we take the radiation. We don't take the full state. We take the state of one pair. So one pair of radiation, you can derive it from the state of from the Hawking state. You can show it's some normalization factor, sum over omega 1, I'll call it, minus omega 1, mass of the black hole, and then minus omega 1 int, and the plus omega 1 out. Okay, just an entangled state, and one has positive energy, one has negative energy. Now we take a black hole, which is a very simple one, very funny toy model, which is made of two particles in a general state which can possibly be entangled. So it's sum over omega, f of omega, omega, and m minus omega. And m is the total black hole mass. Okay? Very simple. We call this particle A, this one is B, so A and B. Now, we have one pair created, so there will be one guy here and another one here. So this is the minus omega 1. This has energy omega. This has energy m minus omega. This has omega 1. Now, this, what does it mean to evaporate? What it means is that those negative energy particles annihilate with the positive energy particles. If they don't annihilate, if the negative energy particles don't annihilate with the black hole matter, then we will have such a state. Maybe it will look, after the full evaporation, it will look like zero mass here. But we will actually have all the matter inside. And then there's no information lost. There's nothing. Everything is still fine, if there's no annihilation. If the matter is still there, the Hawking pairs are still there, then we know that the Hawking inside mode can purify the outside mode. So in that case, there's no information paradox. And the problem is when the actual evaporation happens, which means the annihilation happens. And so what does it mean to annihilate? So let's say this interacts with one of the two particles. Let's say for A for now. You can change the names always, so it's without loss of generality. And they scatter, they make some system together. And that system will have an energy omega minus omega 1. Regardless what it is, the system, it will always have this energy. Because also inside, so T is a killing vector, so E or omega is a conserved quantity, even globally. We write the joint state first of the first pair of radiation and the two particles inside. So we have, let's call this one psi. So it's sum over omega and omega 1, exponential minus omega 1 big M, and then F of omega, and then omega A, M minus omega B, and then minus omega 1 int, and plus omega 1 out. Now, after the interaction happens, we get a state which is similar, but this particle here interacts with A, as we said. So it will be exponential minus omega 1 m f of omega. And then here, we'll have a state which we call omega minus omega 1 A int, which I will define here. Omega minus omega 1 A int is just the S matrix, the interaction matrix, acting on both omega A and minus omega 1 int. So, but the total energy of this I know is omega minus omega 1. Now, we still have this M minus omega B, and we still have this omega 1 out. Please feel free to stop me at any moment. Now, okay, we have this happening. Now we have, okay, the black hole is there, and everything is there, so it will still emit more and more particles, more and more pairs. So then I have another pair created, omega 2 and the minus omega 2. And then these guys interact. You can have this one interacting also with this, and then have another pair created and interacting with. So you can have many scenarios, and then you can easily work out the general one, but for pedagogical reasons, we stick to this. Also because the state will look extremely long. So we have this, so we have exactly this state, but with another omega 2 and with another exponential, which is now minus omega 2 times m minus omega 1, because now the mass of the black hole is m minus omega 1. And then we have here omega 2 and out, and minus omega 2 int. Then after the interaction happens here, if these two interact, then they make a system omega 1, omega 2, and then exponential minus omega 1, m minus omega 2, m minus omega 1, and then f of omega. And then we have the first state, which is already after the interaction with A int, and then the second state. So the system here will have energy m minus omega 2. And then we have one particle outside omega 1 out, and we have another omega 2 out. And this is our state. now we say, okay, what happens when the black hole? So actually, this is what people are doing so far. I mean, at least at Hawking's time. So they reach this point, say, okay, we have radiation particles. If you trace out everything inside, you'll find the outside in a mixed state. And then you find them in a mixed state, and you say, oh, when the black hole evaporates, they are in a mixed state, but there's nothing to purify it. However, it's not like this. I mean, the evaporation is not just tracing out. It's a process which actually influences the state. So what does it mean to evaporate? It means that there's nothing inside. There's vacuum inside. So it means that these people are annihilated. Just means that this is zero energy and this is zero energy. I mean, here after the minus omega 2. So what we have is 0, 0. Then we have some n squared sum over omega exponential minus. This omega 1 is just omega in order for the evaporation to happen. So it's omega m minus. The omega 2 is just m minus omega. So m minus omega and times m minus omega 1, which is now omega. So it's m minus omega squared. And then f of omega. And then we have 0 here, a int. And we have 0, b int. And then we have outside omega 1, which is now omega. And we have omega 2, which is m minus omega. So at the end, we are left actually with a very interesting state, with a very interesting thing. We have this, and this is omega, this is m minus omega. Does it remind you of something? It's Say again?
What we had in the beginning.
Yeah. So it's actually the state inside the black hole matter. So this is just 0, so you don't care about it. This is vacuum, you don't care about it. Both. You have this, which is the same state, but it's swapped to the outside, and it's entangled. And you have only these factors, which are related to the evolution of your system. So you would need more copies of the black hole to actually be able to, or you need to know the dynamics. But yeah, there's a one-to-one map between this state and the initial state. So there's no information loss in this way. And yeah, now maybe we can think what happened here. So the only thing we did is just to take care of the annihilation. And what does it mean to evaporate? It means that there's no particles inside. And then how is this translated in the state? And then naturally you get the entanglement from the inside swapped to the outside. Had we started with a product state inside, just two particles which are not entangled, which is actually included in this case, but I will put it aside, and then annihilated each of them, at the end, it's easy to see that you'll have two non-entangled particles at the end. Yeah. And then, for example, okay, why does this, for example, okay, we have a state from inside and it's getting outside, right? So why does this not violate causality? It doesn't violate causality because nothing is going from inside to outside. It's just the entanglement is being swapped. So it's like a kind of teleportation. Another thing is, for example, why does it not violate monogamy? It doesn't violate monogamy because, and this I really like, it's because the outside particles are only entangled with each other after their partners inside die. So only after the partners inside are annihilated, at that moment, they get entangled with each other. So two people who lost their life partners who were killed inside a black hole suddenly fell in love with each other. Yeah. And what else? Yeah. Tell me.
No. I was thinking like I mean, entangled swap will include some kind of measurements.
Yes.
And this is not
Yes.
entanglement swap. This is kind of unitary, or?
So yeah, this is a good point. So
Because otherwise I will not be able to select, if it were measurements, exactly this state. Again.
yes. So yeah, this is a very very good point and interesting to think about, because so the point here is the following. If you at some early stage, just like now, I have two pairs created, and then I say the black hole evaporated. Okay, this is some kind of measurement, because this is one one out of many possibilities. The black hole at this moment could have not been fully evaporated, because I can also make a measurement and find the created particles are maybe their sum is a half m. Right? So when you do at an early stage, the black hole has the possibility of not being evaporated. So saying that it has evaporated is some kind of measurement or projection. But it's not something, it's just that what evaporation means. It's just that evaporation is one out of many possibilities. However, what you can also show is that, as I said, at an early stage, this is the case. However, if you wait for longer, you have first two pairs created, and there are some branches of the superposition where it's fully evaporated, some branches where it's not evaporated. In those branches where it's not evaporated, there will still be more particles created, and more particles created. And then the probability of being fully evaporated will increase by the time, because it's like a one-direction evolution. It will always go towards the evaporation. It will always be losing mass. And so if you wait for long enough, like 10 times the life of the black hole, the average life of the black hole, then you are infinitesimally close to the evaporated state in all the branches, and you are actually infinitesimally close to the unitary operator, to being unitary.
Okay, I don't know, maybe you answered, but I don't connect fully. So what I'm addressing is really like the crossing points between red and white line.
Yeah, yeah.
This is as far as I understand you, there are...
This is unitary.
This unitary.
Yeah, this is unitary. This is an S matrix. Yeah, this is an S matrix. This is unitary. Yeah.
But at some point you say what is in the cat is 0.
Yeah.
That's the measurement.
That's the measurement. Yeah, yeah. That's the measurement.
So that will be the last step.
Yeah, yeah. Right, right.
Where there is a measurement with one outcome. This is like a down conversion crystal, I understand. Now I'm addressing it. It's just unitary things. You send a laser, you have two photons, or the other way around. Up conversion.
Yeah.
But not measured, I would say.
You don't know that omega minus omega 1 is 0.
How do you know?
I don't know, but then you say if it's evaporated, then it's 0. So if you say it's a measurement, then you are saying just that the evaporation itself is a projection.
Oh, now I'm confused. So because now you introduce measurement with one outcome, which seems like very non-unitary.
It's not. No, it's
same unitarity again.
Yeah. No, this is not a measurement with one outcome. It's just saying that okay. So we work with a black hole, and the black hole is emitting particles. Yeah, and then people say, look at the branch where there is full evaporation. Yeah, and there is a paradox. There is a mixed state. Right, and then what I did is just showing that upon full evaporation, there is no mixed state, and there's the state is actually pure and is one-to-one with the initial state. Now, it's only about having at an early stage of the evaporation process, the full evaporation is one out of many possibilities, because you can look at the black hole and find it not evaporated.
Imagine that you don't get 0.
Very good. You can. It's totally fine. You can not get 0. Okay.
And then it's not evaporated.
It's not evaporated yet. Then that's not a problem. And then when it's not evaporated yet, okay, it will still emit particles. It's quantum Zeno effect if you keep measuring it, but you will not keep measuring it. So if you find it not evaporated, it's completely fine. Then you wait for longer, and then it will emit more particles, and then eventually you'll find it fully evaporated, and then you'll find this state.
Thanks.
You just need to wait for long enough.
Sorry, just for protocol. Zero denotes what?
Denotes vacuum inside the black hole. So it's the state with zero excitations. Yeah, exactly.
You say I keep measuring until I get the result that I like, but this result that I like is then evaporation itself.
Yeah, but it's I mean you don't need to keep measuring. Actually,
No, I'm just
yeah, but in reality, the occupation number of this state is extremely high. So by the law of large numbers, you know that it's almost exactly like the average value of the black hole mass. So even without looking at the black hole, you know how much is evaporated.
Can you use this to reconstruct page curve?
Yes, that's what I'm actually now doing. So what I succeeded already to do is so first taking a large entangled state inside, and then if you condition on, and that's a simplifying factor, if you condition on each Hawking pair, each Hawking negative energy particle fully annihilates one black hole matter particle, then you get exactly the page curve, and that's already done. However, if you want to do it without even conditioning that, so you say I have particles that are created, and then there's probability amplitude of full annihilation, probability amplitude of non-full annihilation, and then you say the mass of those particles increase with time, and show that how the entanglement entropy changes. That's what I'm now trying to do, but not finished yet. But if you condition on every negative energy Hawking particle fully annihilates one black hole matter particle, it gets the page curve. And if I may, I can maybe.
I don't know how long you have to wait. This is not clear to me.
Yeah. So yeah.
Get another result, not zero, because there are many modes. To get zero modes, you wait very long. Like how?
Yeah. So actually, the black hole, the average evaporation time is something like, I think it scales as the mass of the black hole goes as t to the 1/3, if I remember correctly. It goes as I don't really remember, but we have m as a function of t, and we know at which moment it actually fully evaporates. But that's on average. However, because the occupation number of the Hawking state is very large, we know that it's always very, very, very close to the average.
Can I easily see, like, let's assume that the particle that is created immediately annihilates one
Yeah.
so the one that is another.
Yeah.
Can I easily see why I get the page curve?
Yes.
Why are the out particles at first not entangled?
Very good question, yes. Because of the following. Okay, so say you have a large number of particles here. They are all entangled with each other. I'll not draw all of them, but yeah, you know what I mean. They are all entangled with each other. Now, when I annihilate one of them, okay, and then when this is annihilated, then all its entanglements are swapped to this person outside. So this will be entangled with them instead. Okay? So here, the entanglement entropy of the Hawking radiation increased, right? Now, when I have another particle created and annihilates something, then these new entanglements will be swapped to the outside. And then but also the entanglement with this one, right? So there will be very little bit here. But for a huge number of particles inside, with every particle I'm annihilating, there's much, much more particles inside with whom I'm entangled. So with every annihilation, the entanglement entropy of the radiation is increasing a lot. Now, exactly at the page time, when half of the page time is defined as when half of the black hole entropy is emitted, or when half of the black hole mass is emitted. One of them, I think, well, half of the, yeah. So then, and here it's actually the same. Yeah, because just a moment. So the entropy is the area, which is m squared. So yeah, when half of the entropy is emitted. Here, you can see that when half of the matter is emitted, is outside, then with every annihilation, there will be more partners outside than inside. So then with every annihilation, I will be decreasing the entropy. Yeah. And at the beginning, I will be gaining a lot of entropy with every annihilation because there's much, much more inside. So I will be increasing maximally. And at the end, I will be decreasing maximally because most of the particles are outside already. So I will be decreasing maximally. Here, maybe it's not exactly like it's maybe some smoothened page curve in the middle. But yeah. Questions?
So, very nice.
Thank you.
How this, no, I'm very surprised also, but so how this affects the spectrum of radiation, if it is at all, or it is just entanglement between different modes? Because I know that there are other proposals that try to reconstruct to solve information loss paradox by saying, okay, radiation is thermal mode by mode, but there are entanglement between different modes.
Yes.
Is just exactly this what's going on?
Yeah, yeah.
It's also affecting Hawking radiation spectrum.
Okay. Yeah. So you're, yeah. So the thing is, according to this, the state of the radiation at the end will be almost the same as the state of the black hole matter. So before the annihilation happens inside, if you look at the pair, the one outside, the partner outside, you find it in the Hawking state, exactly. But after the annihilation happens, it's and the swapping then happens, then it's as if you picked the particle from inside and you put it outside. So it's no longer in the Hawking state, just because the annihilation itself influences the state of the particle. But I'll think more about this because I'm not exactly sure. So there's this factor also, which is influencing the state. So we need to think about it.
So this, I'm thinking about how this would relate with the generalized second law.
Yes. I'm also thinking about it. And because that actually gives a macroscopic picture and doesn't tell you how the information exactly goes out and what happens. And this actually tells you like what's happening on the microscopic picture. So maybe they can be related. But yeah.
So I agree with that. There should be, when you take the macroscopic average of this, you should
recover that. Yeah.
That's what I'm thinking about.
Yes.
This is consistent.
Yes. That's true. Yeah.
It seems to me that this evolution that leads to entanglement swapping is a particular evolution. So if let's say you write it into the circuit model, and then you have an interaction of like 6 particles there.
Yeah.
And the unitary in between that realizes exactly entanglement swapping. Then for a general unitary, you would not expect entanglement swapping, I would guess. So I think, or do you think you can turn it on its head? So given that entanglement is preserved, what can you learn about the unitary? And the unitary is basically what happens inside the black hole.
Yes. Okay. Yeah, that's actually maybe a very good approach because we haven't found how to actually derive the explicit form of the unitary. So yeah, this might be like an approach to just say, okay, I assume. I mean, after seeing this, then I assume like I need something that does the entanglement swapping, and then try to find the general properties of it. Yeah, that would be a good approach. But
I also find this would be interesting because it's very fascinating. Because I mean, I like the work as well.
Thank you.
So you really have no signal. You are not allowed to signal.
Yeah.
Nevertheless,
Yeah.
you can perfectly send a state over there.
Yeah.
That was on your side.
Yeah.
It's,
So I think the signal here, or like the classical signal, which is usually like in the like teleportation protocols, is actually the full evaporation of the black hole. So what you are doing here is you are waiting much longer than it takes the black hole to evaporate, and then you will actually, that will be longer than the signal needs to actually reach you. Yeah.
because the full teleportation succeeds only when it evaporates.
Yeah, exactly. And the shared, in teleportation, you need shared entangled. You need to share EPR pairs. Bless you. Here there are not EPR pairs, but you share entangled pairs, which are the Hawking pairs. So this is the entanglement. Yeah, this is the entanglement that you are consuming in order to do the teleportation.
Another thing that I found a bit amazing is that it just works to wait long enough. Because usually when you have like a unitary is like you have a Hamiltonian and then you wait a certain amount of time until you like realize exactly that unitary.
Yeah.
But if you wait too long, then like you lose the entanglement swapping or whatever you want to do.
Yeah.
And like here you just wait long enough and it's still preserved.
Yeah.
It seems amazing to me.
Yeah. Here, because at an early stage, if you don't wait for long enough, the evaporation is one out of many other possibilities. So then it's like making a Bell projection on your pairs and on your pair, and you don't know what the outcome will be, or whether there will be entanglement swapping or not at an early stage. But then at a later stage, because you know that each branch of the superposition will eventually emit more particles and then actually eventually reach full evaporation. So you know that this will actually be at the end. I think it's even very interesting to study teleportation in a more general way, which is like in a similar to this case, where you have some scenario where you just need to wait for long enough, and then it's equivalent to having the classical signal. Yeah.
Did you get any feedback from the people?
Yeah, so whenever I send the paper, I asked some opinions. I got negative opinions. Whenever I discussed with people in person, I got more positive opinions. So maybe the paper is not well written, or maybe it's easier for people to communicate.
Did you read the paper, or did you have a chance to talk in the conference or something?
I gave seminars. Yeah. Not a big conference, no, not yet. And yeah, it also took a bit of time to publish it. So at the end, it's now in NJP. But so even in NJP, it took, for example, we sent first, and there are 2 referees, and then like after it was published after being seen by 4 referees.
Were there substantial criticism that you were not understanding?
No.
Mostly not understanding this,
No, I mean, so yeah, someone, one of the referees had absolutely no idea what he's talking about, and then the others were, okay, like raising some points, and we were answering, so it was okay. Yeah. This is live streamed. I shouldn't talk too much. Yeah. I mean, there's a lot also still to do. Like, for example, this is a funny model, right? In reality, particles are not sitting inside the black hole and waiting to be interacted with. There's a space-time inside, and there's some dynamics and evolution. But the thing is, they are in an entangled state. So we need to see how to describe space-times and superpositions, as you guys do, and somehow try to use it as a paradigm to actually do this more properly. And that's one thing to do. Yeah. Another thing is to try to derive the actual form of the unitary operator. Is actually, yeah, there are things which I have already, like, with my collaborators, almost finished, and there are things which are still hard to do. Also connecting it with the what's popular now as like the generalized.
Thermodynamic.
Yeah.
So you can make a tomography of the state inside and let us know, but once it's everything evaporates. I mean, it's really nice.
Yeah. Yeah. But only yeah. Thank you.
Good.
Thank you very much.
So is it not similar to say if I have just a piece of paper and burn it and destroy it,
Yeah.
try to do this quantum mechanics,
Yeah.
describe